Welcome to the deep dive. Today, we're going microscopic, a journey into the world of diffusion.
Okay.
You know how things spread out, like the smell of coffee? It's kind of the same at the atomic level.
Yeah.
Diffusion is all about atoms moving around within solid materials.
Right.
We're diving into these materials science textbook excerpts,
Okay.
and I hear there are two main types of diffusion.
Yes, we've got vacancy diffusion. So that's where the atoms move into empty spaces in the material structure, kind of like a game of atomic musical chairs.
Okay, I'm picturing, these tiny atoms hopping around looking for an open seat. What's the other one?
The other one is interstitial diffusion, and that's where you have these smaller atoms that can actually squeeze through the gaps between the larger atoms in the crystal structure. So like imagine a squirrel. Like a nimble squirrel darting between tree branches. That's kind of like what interstitial diffusion is like.
So it's like two different dance styles at this microscopic party. One's more structured, the other one's more free-flowing. But why should we care about this atomic dance? Does it actually affect anything in the real world?
Oh, it absolutely does. So let's take the example of a case-hardened steel gear,
Okay.
like the one that's highlighted in your textbook. Have you ever noticed how some gears have like a darker outer rim?
Yeah, I think so. Is that related to diffusion?
It is. Yeah, that darker rim is the case. And it's harder than the rest of the gear thanks to diffusion. So during the high temperature heat treatment, carbon atoms from the surrounding atmosphere, they can actually diffuse into the steel surface. And it makes it more resistant to wear and tear.
So that's why those gears can withstand all that stress and friction in something like a car transmission.
Right. Exactly.
Not magic, it's diffusion.
Right.
But how does it work? Do these atoms just teleport to their new locations?
Not quite.
Okay.
So atoms in a solid are constantly vibrating, but for an atom to actually move, it needs two things. It needs an empty space to move into,
Okay.
and it needs enough energy to break free from its neighbors.
So like getting out of a crowded subway car, you need an open door, and then you also need the energy to push your way through.
Exactly.
So temperature plays a big role here, right?
Yeah.
The hotter it gets, the more those atoms are going to be jostling for space.
Exactly. Think about how much faster sugar dissolves in hot tea compared to in cold water.
Right.
It's the same principle. Higher temperatures give those atoms more energy to move around. We even have equations to help us predict how fast this all happened.
Equations. Oh, you're going to have to break that down for me.
Yeah, so we use something called Fick's laws.
Okay.
And they describe how the concentration of atoms changes over time. And this helps us understand the rate of diffusion.
Okay, so if I'm picturing a room full of people, everyone crammed on one side, fixed laws would help us predict how long it takes for everyone to spread out evenly.
Exactly. And understanding those laws is what allows scientists and engineers to control diffusion processes to create materials with specific properties. Like, for example, knowing how fast carbon diffuses into steel helps them create those super durable gears we talked about.
So it's like they're choreographing this microscopic dance to create the materials we rely on every day. It's mind-blowing when you think about it. But this all sounds very theoretical. Are there any other real-world examples where controlling diffusion is crucial?
Absolutely. One fascinating area is the world of semiconductor manufacturing.
Okay.
So those tiny chips that power our computers and smartphones, controlling diffusion is absolutely essential for creating those intricate circuits.
Okay, now you've really piqued my curiosity. I'm ready to dive into the world of semiconductors. Okay, so we're talking semiconductors, those tiny chips that are like the brains of our devices. I have a feeling this is where things get super precise.
You're absolutely right. Creating these chips involves manipulating atoms on like an unimaginable scale.
Yeah.
Like imagine trying to place individual grains of sand in a pattern, but like 1,000,000 times smaller.
Whoa, that's a pretty mind-boggling image. So how do they actually do that?
Diffusion plays a key role. So to make these intricate circuits, engineers introduce tiny amounts of impurities called dopants into specific regions of a silicon wafer. It's like adding spices to a recipe to get that perfect flavor.
Right.
But in this case, the spices are atoms and the recipe is this complex electronic circuit.
So it's all about controlling where those dopant atoms end up. But we can't just pick them up with tweezers, can we?
Exactly, and that's where diffusion comes in. So the process has two main steps, predeposition and drive-in diffusion.
Okay.
In predeposition, the silicon wafer is exposed to a gas with those dopant atoms, and just like we talked about before, those atoms diffuse from the surface into the silicon wafer, moving from high concentration to low concentration.
So those fixed laws are coming in handy again.
Absolutely. They help engineers predict how long it takes for those dopant atoms to reach the right depth and concentration within the silicon.
Okay.
Then comes the drive-in diffusion step. The temperature goes way up,
Oh, wow.
pushing the dopant atoms further into the silicon and locking them in place.
It's kind of like baking a cake. First, you mix in the ingredients, and then you put it in the oven to set.
Exactly.
Okay, so we're controlling where these atoms go. But why is that so important?
Because the precise location of those dopant atoms determines the electrical properties of the silicon, essentially creating transistors and other components that make up that integrated circuit.
Okay, so it's not just about getting the atoms in there, but getting them in the exact right spots to create these circuits.
Yeah.
It's like a microscopic game of Tetris with like really high stakes.
Yeah.
But I have a question about the materials used in these chips. Your notes mentioned aluminum interconnects. Aren't those the tiny wires that connect everything?
They are.
But wouldn't it make more sense to use a more conductive metal for the wiring, like silver or copper? Wouldn't that make the chips faster?
It seems logical, right? But here's where things get a little bit tricky. Remember those high temperatures involved in making the chips?
Yeah.
Some metals, even though they're really good conductors, they tend to diffuse too easily into the silicon at those temperatures.
Oh, that sounds bad.
It is. If the interconnect material diffuses too much into the silicon, it can mess up the junctions and basically break the chip.
Oh, wow.
Think of it like spilling water on your computer. A little bit might not be a big deal, but too much can really cause some damage.
Right.
So even though aluminum isn't the best conductor, it has a very low diffusion rate in silicon,
Right.
making it the safer choice for those tiny interconnects.
So aluminum's like the tortoise. It's slow and steady, but it wins the race.
That's a great analogy. It highlights how understanding diffusion is so important for building the technology that we use.
It's incredible. So the reason our smartphones and computers work is partly because engineers chose a metal that won't diffuse too much.
Precisely. Choosing aluminum is all about preventing unwanted atomic mingling during those high-temperature manufacturing processes.
This whole deep dive is really making me appreciate that hidden world of atoms and how their movements affect, like, the macroscopic world.
Yeah.
But before we wrap things up, are there any other ways that atoms can move around in materials besides vacancy and interstitial diffusion? You mentioned something about shortcuts earlier.
Yes, there are. So while vacancy and interstitial diffusion are the main pathways, atoms can also move along things called grain boundaries,
Okay.
dislocations, and external surfaces. Think of these as like express lanes for atomic traffic, faster routes but with limited capacity.
So even in the microscopic world, there are traffic jams and shortcuts.
Exactly.
But I'm guessing these shortcuts don't have like a huge impact on the overall diffusion process.
You're right. The overall contribution from those pathways is usually small just because there's not as much space.
Right.
However, there are cases where these alternative routes become really important.
Oh, like what?
When we start talking about nanomaterials, materials with dimensions at the nanoscale, those shortcuts start to play a much bigger role.
Why is that?
Because as we shrink materials down to these incredibly small sizes, the surface area to volume ratio increases a lot. Think of it like cutting a loaf of bread into smaller and smaller pieces. You end up with more crust relative to the soft inside. In nanomaterials, there's a lot more surface where those faster diffusion pathways dominate.
Interesting. So those tiny atoms have a lot more options for getting around. What kind of effects does that have?
Well, that's where things get really interesting.
Yeah.
This enhanced surface diffusion can lead to all sorts of unique properties in nanomaterials. Atoms can rearrange themselves more quickly at the surface, leading to faster reactions, and even the formation of new phases that we wouldn't see in bulk materials.
So while these alternative pathways might not be the main players in bulk materials, they become like superstars in the nano world.
Exactly.
It sounds like there's a whole universe of possibilities when we think about diffusion in more detail.
Yeah.
This deep dive has definitely made me want to learn even more.
I'm glad to hear it. And I think our exploration of diffusion today shows how something seemingly invisible can have a huge impact on the materials and technologies that we use.
It's like this hidden choreographer orchestrating the movements of atoms to create everything from the steel in our cars to the chips in our smartphones.
Right.
And with nanomaterials becoming more important, it seems like this atomic dance is only going to get more fascinating and crucial in the future.
I agree.
Well, on that note, I think we've covered a lot of ground today. Any final thoughts you'd like to share before we wrap up this deep dive?
It's amazing, isn't it? We've gone from these steel gears to silicon chips. Diffusion is everywhere.
Yeah, it really is. And understanding how these atoms move at the microscopic level is key to creating these new materials.
It's like we're seeing this hidden dance of atoms that makes everything possible. But before we finish up, I have one more question that's been on my mind. You mentioned that even the smell of cookies spreading through a house,
Right.
or a tattoo fading, that's diffusion too. How does that work? We're not talking about solids anymore, right? That's a great observation. And you're right, we've been focused on diffusion in solids,
Right.
but those same principles, they apply to liquids and gases as well.
Okay.
So like with the cookie smell, those molecules from the cookies are evaporating into the air, and then they diffuse through the air molecules, spreading out from like a high concentration near the cookies to a low concentration the rest of the house.
So those cookie molecules are doing a little dance party of their own, but in the air.
Exactly. And with a tattoo, the ink particles are concentrated in the skin. Over time, those particles can diffuse into the surrounding tissues,
Okay.
which is why we see that gradual fading.
It's amazing to think this invisible process is happening all around us all the time,
Yeah.
even in the most simple things. Any final thoughts for our listeners before we wrap up?
I would encourage everyone to just look around and think about these hidden movements of atoms.
Yeah.
Whether it's metal rusting or a drop of dye spreading in water or even how our bodies absorb nutrients. Diffusion is at play.
Yeah, it's like this secret code that unlocks the mysteries of the world. Well said. Well, I think that's about it for our deep dive into the world of diffusion.
Yeah,
Thanks for joining us.
it's been a pleasure.
And to our listeners, we hope you enjoyed this look into the microscopic world that shapes everything around us. Until next time, stay curious.